Okay, welcome to our Chapter 7 review. This video will cover a quick review of everything we know from Chapter 7 and what you need to know for the test tomorrow and Friday. Okay, so we'll start with exploring exponential models. So the important thing from here is to realize that an exponential function, right, is a function that has an exponent as a variable. Right? What do you need to know? You need to know that x has to be a real number. A, this number cannot be 0. And B, this number right here has to be bigger than 0. And it cannot be 1. All right? Now, we can tell a few things about the function based on what B is. If B is greater than 1, the function models exponential growth. And B, the number B, right, is the growth factor. Right? When B is in between 0 and 1, the function models exponential decay. And B is the decay factor. The other thing we know is the y-intercept is the point 0, a, right there. So a lot of things we can tell about exponential functions just by looking at them. The type of problem that you're going to have to do looks like this. So without graphing, determine whether the function represents exponential growth or exponential decay. So here are the two numbers that we're looking at right here. This is A, that is B. B tells us growth or decay. A tells us the y-intercept. So this would be growth because 1.63 is bigger than 1. My y-intercept point is 0, 129. Right? So no calculations needed here. All you have to do is look at the function and decide growth or decay. So for this function, that number right there, 0.65, tells us that it is decay. And the 2 tells us our y-intercept is 0, 2. All right? For this one, notice that even though it is a fraction, it is still greater than 1. So this represents growth. And of course, that number right there tells us the intercept point is 0, 12. And last function right here on the end is going to be decay. And this number right here tells me my y-intercept. Doesn't matter that it's a decimal. It's still a point. The other kind of question you're going to have is graphing. Easiest way to graph one of these functions is to set up a table. Right? So when you're picking x's for my table, best to start with negatives and positives. We only pick positives for logarithms because you can't take a logarithm of a negative number. But an exponent we can do. Remember, 3 to the negative 2 power equals 1 over 3 squared, which is equal to 1 over 9. Right? And then the rest follows. 1 over 3. Anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. Now let's graph it. We'll graph it in blue. All right, so we start with negative 2 and 1/9. That looks about where that is. 1/3, about a third of the way up. 1, nice and easy to tell where that is. 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry. Whoops. 9. And now let's graph our function. It never crosses the x-axis because that is the asymptote. And there's our function. All right. Remember, all exponential functions look something like this. And depending on how complicated your function is, we'll move it around left, right, up, or down, or reflect it. So this problem, interest problem. If your interest is at an annual rate, compounded annually, we use the following formula. That my amount equals my principal times 1 plus the rate to the t power. So this would change into 2,000, which is my principal, times 1 plus my rate. But you have to put your rate into a decimal. So it becomes 1 plus 0.04. And to the t power, let's start with the first one, 3 years. So working all this out, we get from the calculator 2,000 times 1.04 to the third power, we get $2,249.73. Okay. Now, we do the same thing, only this time we plug in 18 years. So my answer for this one becomes 2,000 times 1.04 to the 18th power. That's 1 and the 0.04 is added together. So we change this to 18, and we get that after 18 years, we have $4,051.63. So obviously you should have more money in your account after 18 years than after 3. So next, 7-2, we're talking about stretches, compressions, reflections, translations, and we know that each one of these in this equation right here do different things. The A is a stretch compression, and if it's negative, it is a reflection. The H moves the function left or right. The K moves it up and down. Right? Finally, if we have an interest problem that is continuously compounded, we have a function that includes the natural log. Or, sorry, not the natural log, that includes E, the opposite of the natural log. And so we'll see a problem with that coming up. First, graph this function from its parent function. Well, we know that it's going to be stretched. We know that it's going to be moved to the right 1. We know that it's going to be moved up 4. So with that, I can make a table and just plug in my numbers. -2, -1, 0, 1, and 2. So if I put -2 into this function, I get 3 times 2 to the -3 power plus 4 gives me 4.375. Okay, next, so -1. 3 times 2 to the -2 power plus 4 equals 4.75. 0 would turn into 2 -1 plus 4. This would turn into 5.5. And all I'm doing is plugging these x's right back in there and just working out the function. 1 minus 1 is 0, so that turns into 1. So 3 plus 4 is 7. And then finally, we can see some explosive growth here. 2, that's going to be 4 times 3 is 12, plus 4 is 16. So we see it goes up quickly after that. Let's graph it. We'll graph it in blue again. So -2, 1, 2, 3, 4.375. Right about there. -1, 2, 3, 4, right there. 0, 5.5. 1, 7, 2, 16 is off the chart. All right. So this one is kind of a little bit harder to get the shape of. I can go back a little bit if I want to. Let's plug, just to get an idea, let's plug -4 back into this function. That gives me 2 to the -5 times 3 plus 4. Okay, so -4, 4.1, boom. That gives me a much better idea. And here's my graph. It looks like this is going to be the asymptote right there. And it goes up like that. Does that make sense? Well, It should, because, look, the function has been moved 1, 2, 3, 4 spots up, and it's been moved about 1 to the right. And if we put it back there, where it goes, sorry, 1 to the left. And that's my graph. Make a table, plug in the values. Okay? Here, we see continuously compounded. That means that we need to use the function with e. So that equals principal, e to the RT power. So my principal is 2,000. E, my interest rate, change it to a decimal, 0.51 times 3 to the t power. Working this out on the calculator, gives me that after 3 years of continuous compounding, 2,330.65. So $2,330.65 after 3 years with continuous compounding. Okay, to logarithms. So, logarithmic function is the inverse of an exponential function. The graphs and functions are reflections of one another across the line y equals x. Logarithms can be translated, stretched, compressed, or reflected as represented by this formula, where h moves left and right, k moves up and down, and a is a stretch or compression. Okay? When the base of a logarithm is 10, it's called a common logarithm, which you do not have to write the 10, as shown here. Okay? So the kind of questions that you're going to have, first of all, is to change each of these to logarithmic form. So, what do you have to do? There's the base. So this turns into a log, base 7 of 49 equals 2. Just rearranging, no calculations, just rearrange the formula, rearrange the expression to make a logarithm. This is log base 10, so I don't have to write it. So the log base 10 of 1,000 is equal to 3. I do not have to write a 10 if it's base 10. This is the log base 5 of 625 equals 4. The log of base 5 of 625 is the exponent 4. Answers to logarithms are exponents. The log base 10, so I don't have to write the 10, of 1 over 10 is equal to -1. Okay? Next, describe how this function is translated. Well, this means right here that it is up 1. Okay? The -5 tells me that it is right 5. The 3 tells me it is up 3. This -2, because it's in parentheses, tells me that it is right 2. This +2 in parentheses tells me left 2. This tells me down 1. So that's how the translations work. Up, down, left, and right. So, the opposite of this page, changing everything to a logarithm, this page we're changing it to an exponent. The base is here. The exponent is here. The answer is the big number on here. So we have 2 to the 7th equals 128. For this one, there is no base, which means base 10. So 10 to the -4th power equals 0.0001. For the next one, we have base 6 of 1 is equal to 6. And base 4 of 0 is equal to 1. And notice that all of these actually work. They make sense. 2 to the 7th is 128. So if your answer does not seem to work out, you probably wrote it wrong. Okay. Most of the questions on the test are going to deal with the following properties and how to use them not only here, but in an equation. We have the product property, where if you see a plus, that can change to multiplication, or the other way around. If we have division, changes to subtraction, or subtraction changes back to division. And this is the most important one. If you have an exponent, it goes in the front, like here, okay? Like there. So any exponents change into coefficients by the power property. So here, single logarithm. We're making everything into a single logarithm. I see a negative, I see a minus, I see a plus, I see a number in the front. So I'm going to use all three properties. I'm going to use the power property, product property, and quotient property. And to turn this into a single logarithm, we're going to change this to 8 over 6 squared times 3, which in turn, 8 times 3 is 24 over 36, which is, we'll write underneath, log of 2/3. Okay? The negative right there means quotient rule. So I take the 4, I bring it to an exponent, and I get log of m to the 4th power over n. That is the quotient rule and the product rule. And the last one, same thing, quotient rule and product rule, only this time is log of 5 over, this is the base. The exponent goes over here. So it turns into 2 to the k power. The opposite of this is to expand these logarithms. So expanding them, I see division, that means subtract. So that's log base 5 of r minus log base 5 of x. And I'm going to have to go down a little because these are going to get long. Here we go. Log base 3, sorry, the 2 comes over here. So it's 2 log base 3 of 2x. And that's simplified enough. You can separate that a little bit more, but we'll leave it like that. For this one, we can do 2 log 7, log base 3, 7, 2x minus 3. And I can split that into, 2 also. So this could be log base 3 of 7 plus 2 log 2x minus 3. All right, and then for this one, I'm just going to bring this down over here. We're going to do this one, takes up the most room. So let's split this up. Okay, 2 on the top, 1 on the bottom. So it turns into 2 log A plus 3 log B minus 4 log C. And that's how we split that one up. Okay? Finally, exponential and logarithmic equations. Okay? Logarithmic equations, an equation with the form of b to the cx, variable in the exponent. It's an exponential equation. If it has a logarithm in it, it's a logarithmic equation. Use logarithms to solve exponential equations. Use exponents to solve logarithmic equations. So here we go. Solve each equation. This one's easy because we can use the same base. Right? So 2 to the x, I can change 8 to something with a base of 2. It becomes 2 to the 3rd. If the bases are equal, the exponents must be equal. X equals 3. 27, the next one, 27, I can change it to something with a base of 3. Equals, well, that's 3 to the 3rd power. If the bases are equal, the exponents must be equal. So x is equal to 3 over 2. And lastly, right, 4 to the 3x, 64 is 4 to the 3rd. So 3x is equal to 3, x is equal to 1. Right? This will, however, get slightly harder. When you don't have the same base, round your answer because you're going to have to use a logarithm to solve. So in order to solve this, we take the logarithm of both sides. Okay? Why do we do this? Because of the power property. Now the x can come out front. Log 2 equals log of 3. And now I can divide both sides by the log of 2. Log 2's cancel out. X is equal to log of 3 divided by log of 2. And the answer is 1.58, about. This one follows the same way. Take the log of both sides. Okay? Use the power rule to bring the x out front. So x log 4 equals log 19 divided by log of 4. All right, that cancels that. X is equal to log 19 divided by log of 4, which gives me 2.12. Now, the last one tells us an important thing. Get the exponent, get this term, the term with the variable in the exponent, get it by itself first. So we subtract 8 from both sides. We're left with 10x. 10x equals 1,000. And now look at the 1,000. It has a base of 10. So this question just got a lot easier. 10 to the third power. So x is equal. So whether or not you have to take a logarithm of both sides, or the problem has a common base, we can solve exponential equations using those two properties. In this question, all you have to do is plug in population. World population equals what? The population is 8 billion. So 8 equals 6.72 times 1.014, 14 to the x power. So now here, when you have a problem like this, the first step is to get this term by itself. Divide by 6.72. That cancels that. And we're left with 8 divided by 6.72 is going to equal 1.19 equals 1.014 to the x power. To solve, we take the logarithm of both sides. Why do we do this? To use the power rule. To take the x out of the exponent and put it in the front. So the log of 1.19 equals x log 1.014. Divide both sides by the log of 1.014. Divide this one by the log of 1.014. And we get an answer from our calculator. 1.19 divided by log of 1.014. And we get 12.5 years, which means after the year 2000, so the answer is going to be 2012, halfway through 2012, July 2012. Right? The opposite is also true. So to solve logarithmic equations, use an exponent. The base here is 10. So 10 to the negative 1 equals 2x. 10 to the negative 1 is 1 over 10. Divide both sides by 2. X is going to equal 1 over 20. Same thing on this side. All right? First, use the power rule. We put the power up there. X plus 1 squared. The log of x plus 1 squared equals 5. That's the base 10. So 10 to the 5th equals x plus 1 squared. We take the square root, and that gives us. Now, because we're taking the square root, it's the positive and negative of 5 over 2 equals x plus 1. Subtract 1 from both sides. All right, and now we're going to get two answers. Negative 1 plus or minus 10 to the 5 over 2 power, which is about 316. Okay. So the answer equals x. So my answer is going to be about 315 or negative 317. Either one of those. About. Okay? Good enough to round. Now when you have two logarithms, you must combine them into one. So this means multiplication. So it would be the log of 2x squared equals 11. Base 10 to the 11th power equals 2x squared. All right? Divide by 2, take the square root. In this case, it's going to be a very large number. Divide by 2, take the square root. So x is going to be equal to 10 to the 11th power divided by 2, take the square root. So we're going to be about 223,607. About. I will try not to put a question that is that ridiculous. Right? And the last thing we talked about is the natural logarithms, which is just a special kind of logarithm with a base of e. That is a natural logarithm with a base e. You could write it with the natural logarithm ln. Right? Same way as we write common logarithms, you don't have to write the base. So you see something with a natural log, that's a base e to the 6th power equals 3x. Divide both sides by 3. X is going to be equal. E is just a number. So it is e to the 6th power divided by 3, which is about 134. Okay. We do the same thing over here. E to the 36th power is equal to 4x minus 1. Add 1 to both sides. Right, so we have e to the 36th power plus 1 equals 4x. Divide by 4. We have x is equal to e to the 36th power plus 1. Divide by 4. We have a very big number, and we'll try not to do it. 1 times 10 to the 15, about 1.07 times 10 to the 15. Big number, lots of zeros. Okay. Finally, we have a question like this, a physics question. I wouldn't go through this, but number one, I'm running out of time. Number two, I didn't put on your test. So if you want extra credit later, you can take a look at this. But for now, that is your test review.